Hello, good morning, everyone. Can you hear me clearly? Good morning, everyone. Yeah, I realized our physics class is very early, right? On Monday. So I'm not sure whether you guys find it difficult to wake up so early. Okay, very early, huh? Okay, so today we are going to move into can consider a totally different topic, or what we can say is what physics 062 is focusing on, yeah, on electric current. Then from today onwards, then you will notice that all the subjects, all the topics are related to electric, either on the macroscopic or microscopic level. Okay, so I'm going to share the content. Oh yeah, before I start, just a reminder to your project, yeah. So far only 2 groups have shared their Google Drive. I think one is Dynamics, can't remember. Milk Tea. One group is Milk Tea. The other one is Anonymous. Okay. There are 5 groups altogether. So if your group you haven't shared the Google Drive, please quickly share the Google Drive to me and Miss He, and also check the comment. Okay, please go to Moodle under update for project. Okay, check the comment file posted by Miss He. Okay, now is week 4. So you have already completed half of the semester for this semester. So you must quickly catch up on anything that you missed, especially on the project. Yeah. Okay. So today we are going to cover electrostatics. So there are 4 new terms that we want to introduce to you. The first one is electric force. Okay, you have learned about different types of forces already. You have learned about frictional force, gravitational force, what else? Push, pull, normal force. Okay, so today we want to introduce you to electric force. Then after learning electric force, another term is electric field. Okay, then the third one is electric potential energy. Okay, you have learned a few energy as well, thermal energy, potential energy, kinetic energy, what else? Elastic potential energy. So today is electric potential energy. And the last term is electric potential. Okay, so I hope you guys can pay attention to what these 4 terms are about. Okay, so learning outcomes is a very good way for you to check after every topic, see whether you have understood all the scopes that we cover for that particular topic. Okay, so here you will see that, okay, the first one, we want to state and apply Coulomb's law. So what is Coulomb's law about? And then what is electric field of a point? Okay, see here, electric field, Coulomb's law. Okay, and then how to relate electric force and electric field. There is a relationship. And then what is the conductor, and what is the electric field inside a conductor and around a conductor. Then determine the electric field. How do we calculate electric field between 2 parallel plates? Then the 6th one, electric potential energy. And the 7 is, what does it mean by electric potential? Okay, so the 4 terms here. Then the 8 is find the work done to move a charge through potential difference. And then the last one is the electron volt, okay, EV, how to relate it to energy in joules. Okay, so here we have some particles, okay, the round one, we have some particles. So if the particle is neutral, so it means that the positive and the negative charges, they are all evenly distributed around the particle. Okay, so for example, let's say we have, so okay, so if you have two positive charges, then you will have two negative as well, so that the particle will be neutral. So let's say, oh, these are like this, you have okay. Then if I bring a plastic ruler, for example, and then I rub the ruler. Okay, I bring a ruler here, then I rub it with a piece of cloth. For example, let's say I have a cloth here. Okay, then I rub the ruler. Let's say this is a ruler. Okay. So I rub the ruler, then the ruler will become negatively charged. So here, yeah, okay. So you have a lot of negative charges here. So negative charges, then it will attract, okay, the particles here. Just now we said particles, it is neutral. So it has positive and negative. So if I rub the plastic ruler, then it becomes negatively charged. So this negative charge is going to attract positive or negative charge from the particles. What do you think? Is it going to attract the positive or the negative charge from the particles? Particles are the round one. Negative is going to attract the positive, okay? So the positive and the negative charge within the particle are going to rearrange themselves because the positive charge notice that, oh, somewhere near me, okay, neighboring area, there is negative charge. So the positive charge will be attracted. So yeah, the positive charge will rearrange themselves, something like this, okay? Yeah, so that later on, they will be attracted. Okay, so yeah, so you see, just now we said the ruler, negative, negative. So the positive here will be attracted. Okay. All right. So from here, we want to introduce you to electric force. Okay, electric force is actually discovered by Coulomb. Okay, so what does it say? It said if the two charges have the same sign, either positive or negative. Yeah, if having the same sign positive, then or the same negative, then they will experience repulsive force. Okay, so let's say you have a positive and positive. Okay, so they will not attract each other, but they will, yeah, they will go different way. They will repulse each other. Okay, same goes to if you have negative and negative, yeah, it will also be like this. All right, so if you have the same sign, you will experience repulsive force. Okay, but if the two charges they have opposite signs, then they will experience attractive force. Opposite, then they will experience attractive. For example, you have one positive and negative, yeah, and they will be attracted to each other. Okay, so positive will be attracted to negative, negative will be attracted to positive. Okay, so Charles Coulomb deduced, he found out electric force, this one is electric force here, yeah. So electric force is directly proportional with the product. Product here means multiplication, okay? Product of two charges. Okay, so for example, if you have two charges, let's say you have Q1 for charge 1, okay, and then Q2. So it says here, Q1 times Q2. Okay, so force, electric force is directly proportional. Product means multiplication. So you notice that I multiply Q1 and Q2. So directly proportional. But electric force is inversely proportional with the square of the distance between the two charges. Distance, then we use R, okay, square. So you put a power of 2, okay? So this one, if you combine them together, yeah, then it becomes like this, okay? So for electric force is directly proportional to the product of Q1 and Q2, but inversely proportional to the square of the distance. So this is relationship. So if we want to change it to an equation, then we normally need to include a constant. So in this case, the constant that we use is K, okay? So K Q1 Q2 divided by R squared, okay? So this is Coulomb's law, okay? F equals to K. K is a constant. And later on, we'll tell you what is K representing. So this K is not what you have learned previously under ideal gas law, okay? Ideal gas law, the small letter K is Boltzmann's constant. So this one related to electrostatic, this is another K, okay? So electric force, it has a symbol of F, and then the unit for force is Newton. Okay, so you see here, if the same charges, they repel, okay? So it will be repulsive force in between them. But if it is different charges, positive and negative, then they attract each other. So we say same charges repel, but unlike charges, they attract each other, okay? So how do we tell which force we are talking about? So you see here, electric force on Q1 due to Q2. So if you have two charges close to each other, so they will have forces between them, either attracting or repelling each other. So if I want to say, okay, what is the force experienced by Q1, okay, due to Q2? So we will write F12. Okay, I'm talking about, I want to know about electric force on Q1, charge number 1. So I'm going to write due to charge number 2, because charge number 2 is somewhere near Q1. So I will write down F12. Okay, but if the other way around, let's say I want to calculate what is the electric force on Q2 due to Q1, then I will have to write down, let's say, electric force on Q2 due to Q1. Okay, then I will have to write down like this, F21. Okay, so this is electric force on Q2 due to Q1. All right, so equals to, but you will notice that the force, the electric force is going to be the same for both of them, either on Q1 due to Q2, or it is on Q2 due to Q1. Okay, but the direction is going to be different. All right, so same goes for the unlike charges. Okay, electric force on Q1 due to Q3, then we will write down F13. All right, so it is K, and then Q1 multiplied Q3 divided by R squared. Okay, so electric force is a vector quantity. So vector quantity, what does it mean? Vector, then you will have magnitude as well as direction. Okay, so you see here on the same charges. So what is the electric force felt by Q1, yeah, due to Q2? Because they are same charges, so they repel. Okay, so Q1, it will feel that it is being pushed away by Q2. So you see Q1, the direction of the force is to the left. But on the unlike charges, okay, Q1 and Q3, they attract each other because this is unlike charges. Okay, so for Q1, the direction is it will feel that it is being attracted to the negative charge. So the direction is to the right. But if we are looking at the negative charge, so this negative charge will feel that, okay, it will feel that, oh, it is being attracted to the left. Okay, so the force, the direction will be different. Okay, but when you are calculating the electric force, the magnitude between two charges, then it will be the same, but the direction will be different. Okay, so K here is actually Coulomb's constant. So it is 1/4 pi and then epsilon naught. So this epsilon is permittivity. Okay, this one, permittivity of the free space, and it has a constant 8.85 times 10 to the power of -12. But normally we do not use this. We directly use K equals to this one. Okay, so K equals to 9 times 10 to the power of 9 Newton per this one is a Coulomb. C is the unit for charge. Okay, Coulomb square and then meter square. Okay, so Q1, Q2 are the charges on charge Q1 and charge Q2, and then R12 is the distance between the two charges, and R13 is the distance between Q1 and Q3. Okay, so remember, distance, the SI unit is meter. So if it is not given in meter, what you need to do is to do unit conversion, change it to meter. All right. Okay, so now you have been introduced to this. So now we want to try to solve a problem, calculating electric force. Okay, so some steps in solving electric force problems. First, you have to identify the direction, okay, because we know that electric force is a vector, so it has magnitude as well as direction. So direction, how do we determine the direction? You have to remember that same charges, they repel, okay? Unlike charges, then they will attract each other. Then we determine the magnitude. So when you are calculating the magnitude, no need to consider the direction first. After calculating magnitude, then we determine the direction, whether to the right as positive or to the left as positive, or up or down as positive. Okay, then we calculate the net force. This is how we calculate for a vector. Okay, especially if they are not directly on the vertical or the horizontal axis. Okay, if they are at an angle. Okay, so you look at the question here, right? So we have the question is, what is the electric force on a positive charge? Okay, positive, so you have a sign here, positive. Two, okay, nano n here, small letter n here. This one is nano, yeah. So nano is times 10 to the power of -9. Okay, position at O. Okay, at origin position here. So now how do we calculate this one? It is it wants us to determine the electric force on the positive charge at position O. Okay, so now we want to determine electric force on O due to Q1 and also due to Q2. Okay, so Q1 is a positive charge, Q2 is a negative charge, but the charge at position O is a positive charge. So you see here, positive and positive, then they will attract or they will repel. You have same charges here. The positive charge, this one here is positive 2 nanocoulomb. So positive and positive. So this positive charge due to Q1, it will be repulsive force. But this 2 nanocoulomb, the positive charge due to Q2, the negative, is going to be attracting each other. Okay, so because of Q1, so the force, the direction that is going to be experienced by the positive charge is to the right. Okay, it will not be to the left. Q1 and the positive charge, yeah, this one we call it positive charge, the one at O. Q1 and positive charge, they are on the same line, right? We can consider they are on the same line. So the direction of the force is either to the left or to the right. But if you look at Q2, the negative charge, you see this one? It's like this, isn't it? Between them, okay, they are not vertically together, and they are also not on the horizontal axis. But this one is with an angle. This one is at which quadrant? The second, third. At the third quadrant here. So positive and negative, so they will attract each other. So the direction by positive charge will be right? Yeah. So the positive charge at position O due to Q1 is to the right. But due to Q2, the negative charge is to the, this one is southwest, okay? Southwest direction. So you have, let's say we are taking, I'm taking Y up as positive. I'm taking X component to the right as positive, okay? So now you will notice that the direction, okay? The direction due to Q1 is to the right, okay? So this one is exactly on the horizontal x-axis. But the one due to Q2, the negative charge, okay, the southwest, oh, this one is not on Y and also not on x-axis. So what do I need to do? We need to resolve the vector. So if we need to resolve the vector, okay, so I hope you still remember when we resolve, then we will get this. Okay, we will get this. Why do we get this? Because this is head to tail, right? If I, let's say here, I go this way, then I go down, then eventually I will still get to this point, correct? So now I just move the vertical one to the other side. Okay, so that is why. So I move this one, yeah? Yeah, so that is why you will get the original, the vector is in between the x and y component. Okay, so this is the y component. Okay, y is the vertical one, and then the x component is the horizontal one. Okay, along the x-axis. Okay, so first we want to calculate the magnitude first. Okay, just to calculate the magnitude of the electric force. Okay, so this one is, we are talking about positive charge at position O due to Q1 or due to Q2. So let's say I'm just assuming this one is O, okay? So due to Q1, okay? So, okay. I'm assuming this one is QO, okay? And then due to Q1 divided by R squared. Okay, so what is K? K is 9 times 10 to the power of 9. So I multiply QO is 2 nano, okay? And multiply Q1 is 6 nano. And, okay, nano, you have to multiply 10 to the power of negative 9, yeah? And then the distance between them, okay, look at the distance. This is 4 centimeter. Remember, we said the distance R has to be in SI unit meter. So 4 centimeter will be 0.04 and then a square. Okay, so this one you calculate, you are going to get 6.75 times 10 to the power of negative 5 Newton. Okay, so I just calculate the electric force. So now I want to calculate the second one due to Q2, the negative charge. So the positive charge due to Q2. So also the same. Okay, this time I'm going to write it down. Okay, the nano. And okay, this one is -8. Okay, when we calculate the magnitude, ignore the positive or the negative sign first, because the positive and the negative later on, we are going to include it for the direction. So when you are calculating the magnitude, ignore first, yeah? Ignore positive or negative sign of the charges. Just calculate the magnitude. Later on, we include the positive or the negative, yeah? So this one is 8 nano. And then the R. Okay, what's the distance between the 2 nano, the positive charge and the Q2? Over here is the horizontal distance is 4 centimeter, vertical is 3. So what is the hypotenuse here? Can get this one? You are going to get this is 5 centimeter. Any idea how to get this one? This is 4 centimeter. This is 3. How do you get this one? Your trigo, right? Still remember your trigo? Let's say this is A, this is B, then this is C. So C equals to A squared plus B squared. This one, right? So you calculate, then you will get 5, all right? So 5 centimeters, so it becomes 0.05 squared. Okay, so this one you are going to get 5.76 times 10 to the power of -5 Newton. Okay, so we have calculated the magnitude. So now we want to resolve, okay? Especially we want to resolve for F02 because F02 is not along x-axis, neither it along y-axis, okay? It is at an angle, so we have to resolve it. So remember the direction that we have taken as positive, okay? Y up as positive and then x to the right as positive. Okay, so I'm going to draw a table here. Okay, so this is your x component, y component. Okay, this is your electric force. So we have two, right? One is the F01. Okay, F01, just now we have drawn, just for you to look at the direction. We have drawn it to the right, right? And then F02 is, this is southwest. Okay, this is the direction. And then F02, the direction is like this, right? Okay, and now we have also said that we are going to resolve this one to be this way. Okay, so now, what's the value again? Just now, this one is F01 is how much? 6.75 times 10 to the, okay, I will write down here. Yeah, this one 6.75, this one and this one, yeah. So this one is x component. My direction is like this, y and x positive, okay. So this one is x component because horizontal along the x-axis. So I have 6.75 times 10 to the power of -5. Okay, this is positive. Okay, if you want to ignore putting positive, it's okay. All right, but if it is negative, make sure you put a negative. All right, it's not positive because it is moving to the right. Does it have a y component? No, it doesn't have a y component. This is only horizontal, so the y component will be 0. All right, then we look at the F02. Okay, F02, what we have got is 5.76 times 10 to the power of -5. So now if we want to get this one, the x component, the horizontal one, so how do we calculate this? still remember the triangle is like this, right? This one 5 centimeter. This is 4. This is 3. Okay. So if I want to get, okay, let's say angle here. So do we need to get, this is cos or sine? I want to get the x component, yeah? This is your x component. This is your y. I want to get x component. So this will be 5.76. Okay, tell me, is this going to be cos theta or sine theta? Theta is here. Cos theta or sine theta? Cos, okay? Because this is adjacent. The x component for F02, okay, for the electric force of F02, the x component is actually adjacent to the angle theta. So adjacent, it is cos. If it is opposite, then we use sine. So in this case, we are going to use cos theta, okay? Cos theta equals to what? In this case, we do not have to really determine the angle because we know about the adjacent, the opposite, and also the hypotenuse, right? We know the length. So we can directly use it. So cos theta is actually 4 over 5. Then sine theta will be 3 over 5. Okay, so we use it directly. So this one is cos theta. Now, here is where you need to put a positive or a negative for the direction. Now you look at the x component for F02, pointing to the left, which is opposite, okay, in opposite direction of what we have indicated as positive. We want to go to the right as positive. So this one is negative, okay? Why is it negative? It's because it is moving to the left. Okay, so this one you are going to get, you calculate this, you are going to get cos is 4 over 5. Okay, so you are going to get negative 4.61. Okay, so this one is pointing to the left. Okay, then we do for the y component. Y component is pointing down, okay? So pointing down, then don't forget to put a negative in front because it is pointing downward, all right? Okay, so this one equals to, sine is 3 over 5. So you will get negative 3.46 times 10 to the power of negative 5. So this one is pointing downward. Okay, you always compare it with what you have indicated here. This is your indication of direction. Which one you want to take as positive? So after getting the x and y component for both of the electric forces, then we want to get the net. All right, so you can draw a line here. Okay, so now I want to get okay, so I will have, so you just add them up, okay? So if positive on this one, so 6.75. Okay, this is positive, but this is minus, right? The 4.61 is negative, so you minus. So equals to, this one you will get equals to 2.14 times 10 to the power of negative 5. Then Fy, you have 0 minus 3.46. All right, so this one in the end is positive, right? So it means that it is pointing to the right. And this one still negative, so it is pointing downward. Okay, so after getting this, then we want to get the net force. Okay, so how do we get the net force? Just like how we calculate the A square plus B square equals to C square. Okay, so now the force is like this, yeah. Your force is like this. This one is pointing here. This is your Fs. Okay, and then this one is down. This is your Fy. So we want to get this one. What is your F net? Okay, so F net square. Okay, and then this one also square. Then you are going to get, you just substitute the value, yeah. I have already shown you what is the net x component and also net y components. All right, so you just substitute into the equation and you are going to get 4.06 times 10 to the power of -5 Newton. Yeah, so this is the net electric force on the positive charge at position O, okay, due to Q1 and Q2. So now if we want to determine the direction, okay, so let's get the direction here. Get this one, alpha, okay? So how do we get this one? You have the x and you have the y, right? We can get tangent. Remember what is tangent? Tangent is the opposite divided by the adjacent. Tangent alpha equals to opposite divided by adjacent. So the one that is opposite is Fy and adjacent is Fx. Okay, so this one, it means that you are actually when you are calculating the angle, you can ignore the ignore the negative sign. Just calculate, get the angle, then later on from here, actually from the positive and the negative, I have already shown you, okay, which direction it is pointing, so you can know where is the angle located. Okay, so when you are calculating to determine the angle, ignore the positive or the negative sign. Just get the magnitude. Okay. Fy is 3.46. This one is 2.14. Okay. So you are going to get the angle is, so the angle will be 3.46 divided by 2.14. Then get the tangent. About 58.3 degree. Okay, so it means that this angle here, is 58.3 degree. Okay, all right. Any question? Okay, so this is very important when you are dealing with a vector that is not exactly on x or on y direction, yeah, or on x or y axis. Then you have to resolve it to x and y. Just remember, when you resolve, the x and y must be the x and y component. You look at the FO2 here, the x and y, which is in blue color, they are actually perpendicular to each other, right? If you cannot draw it directly like this, you start by drawing from head to tail, okay, then head to tail. Then you will also get it in this direction, okay? All right. So now we want to introduce, move on to the second term, electric field. So what is electric field? Electric field, let's say you have a charge, okay? You have a charge position at somewhere. So the region around it, okay, the region around that charge, okay, it will have this electric field. So if you have another charge, okay, coming near you, okay, coming near the charge, then it will feel this force exerted on it. Okay, so for example, let's say you have a charge here, for example, positive, yeah, then around it, okay, this region here, there is electric field. Then if another, let's say another, a small charge here, maybe a test charge, okay, it comes near the region, then it will feel, let's say this one is positive. If it is positive, then it will feel attractive force or repulsive force. If the test charge coming here, the red dot, is positive, so what kind of force is it going to experience? Attractive force or repulsive force from the charge? Attractive or repulsive? Repulsive. Okay, let's say this one is positive. Then it will feel, it will feel like this. Okay, repulsive. All right. But if it is negative, let's say I have another one. This one, let's say negative. Yeah. Then it will feel, will feel this way. Okay. So electric field is actually a region around a charge. Okay. Within which, if you have another one coming, what kind of force is it going to experience? All right, so this is electric field. Okay, so it is actually the force felt by a test charge, then divided by the magnitude of the test charge. This one then, electric field, what is the symbol that we use? Is E. Now this one, don't confuse it with energy, yeah? Energy, we also say, generally energy, we also use E, isn't it? But here, E, we want to use it to represent electric field, all right? So electric field has a symbol of E, and then the unit is Newton per Coulomb, okay? So the unit is Newton per Coulomb. So electric field line always point out from a positive charge, but then point in to a negative charge. So this one, just now the force felt, okay, this one, yeah, is like this. Electric field is actually the force, okay, the force felt by the test charge divided by the magnitude of the test charge. Okay, the test charge, this one is Q, this one small q here, another small q here, one is positive, one is negative. Okay, so the force experienced by the test charge divided by the magnitude of the test charge. So when it says magnitude, it means that you do not have to include the positive or the negative sign, yeah, just get the magnitude. And over this one, if positive, then it is always pointing outward, yeah. For example, like this. Okay, then if you have a negative, it will be pointing inward. All right. Okay. So this one is test charge, yeah. Test charge is the one that coming near the original charge, yeah. It is being placed at a position. Test charge at a distance, or maybe position, or for example, okay. So the Q is not the test, it's not the charge, the one positive here, yeah. This one, then we use Q. This one we use Q. So the one that come near you, that one is the test charge. Okay. All right. So electric field always, you have to draw it radially outward from a positive charge. Then if it is a negative charge, you draw it radially inward. So the P, this one is your test charge. It's a test charge, yeah. What is the force felt by the test charge due to its position? So electric field at point P due to Q1. So how do we write it? We write it as E1, okay, due to Q1. Then if it is the one on the right hand side, electric field at point P due to Q2, then you can write down as E2. Okay, so you look at the direction. Electric field is also a vector. So again, a vector, then it has magnitude as well as direction. So electric force is a vector. Electric field is also a vector. Okay, so you not only need to calculate the magnitude, you also need to determine the direction. So if the test charge is at point P, so the electric field, okay, the direction of the electric field will be, which quadrant? First quadrant will be, this one is northeast, okay, pointing northeast. And if you look at the right hand side, electric field at point P due to Q2. This one, you see, pointing in, okay, because the charge is a negative charge. So the test charge positive, so it will be feeling that it is being attracted towards the negative charge. Okay, so pointing, this direction is southwest. Okay, so again here, E equals to KQ1 over R. Generally, yeah. Okay, and then just the charge, okay, Q1 only. You do not have to include the charge for the test charge. All right, just now the electric force, we say it is KQ1 Q2 divided by R squared, right? So now electric field, because electric field is a region surrounding a charge, okay? So this one, then we only need to consider the charge, okay? So just the charge Q1. So you do not have to consider the test charge, the one that coming near you, all right? So it is very similar. If you look at the equation, yeah, just the Q2 is being taken out. So this one, electric field is KQ1 only divided by R squared. All right. So if the charge is with a symbol of Q2, then you use Q2. Okay. If it is Q1, then you use Q1. All right. Any questions so far? Okay. Today you will notice that the formula, they are very related to very similar to each other. One is you take out a Q, then later on you will notice that, oh, the other one for electric potential energy and electric potential, we take out the R square. It becomes only R, right? Okay, so now we want to solve for electric field. Still the same question, okay, still the same diagram, but now we want to calculate the electric field. So first of all, when we are solving electric field, just first you determine the direction, but when we are calculating the electric field, do not include the positive or negative sign, just calculate the magnitude. After that, when we are resolving the vector, then we include the positive or the negative, okay, to tell about the direction. So over here, magnitude, so ignore positive or negative sign of charge first, okay? Later on, we include the positive or negative. Okay, so this one, if we look at the test charge, okay, the test charge is at position O. Okay, what is the electric field at position O? Electric field here. There's a dot here, and then subsequently we want to find the electric force. So just now the first word example, we have already calculated electric force. So now in this case, we are calculating from electric field. Then we calculate electric force, and then we want to check, see whether the answer is going to be the same. Okay, so there is a positive charge. This one here is actually a positive 2 nano coulomb. It is being positioned at O. So how do we calculate the electric field? Okay, so now for positive charge Q1, okay, Q1, then the electric field will be pointing outward radially, isn't it? Pointing outward. So for the test charge at position O, it is of the same charge, right? Positive and positive. So it will feel what? It will feel this way. Okay, it will feel like this. And then for Q2, the electric force is this one. The electric force is going like this, okay. And then for this one is going in like this. Okay, that is the electric field. So for charge, the positive charge, okay, 2 nanocoulomb at position O, due to Q2 is going to be attracted because they are of different charges. One is positive, the other one is negative. So again, this one will be this way. All right. So again, you notice that the direction, okay, the direction for positive charge, okay, 2 nanocoulomb due to Q1, okay, is on the same x-axis, along the same line, horizontal. But then due to Q2, is not along the x-axis or along the y-axis. It is at an angle. So what we need to do is resolve. All right. So you see this one? I have to resolve as well. So the vector is pointing southwest. So I will just draw the x and y component. Make sure x and y component are perpendicular to each other, and then they cover the vector. Okay, so this is the y component. This is the x component. Okay, so first of all, before we move on to resolve them, we just calculate the magnitude first. All right, so I'm going to calculate the magnitude. So E at position O due to Q1. If you want to write down as EO1, also can. Otherwise, you can just write down as E1. Okay. So this is the electric field. Okay. On this positive charge, 2 nanocoulomb due to Q1. So K Q1 over R squared. This is 9 times 10 to the power of 9. Okay, Q1 is 6 nano. Okay, and the distance is 4 centimeter. So change it to meter square. Okay, so this one you calculate, you are going to get 33.75. You are going to get this one. And then we calculate the electric field on position O due to Q2. So I write down 2. So this one now I have to use Q2, okay? Ignore the negative, yeah? Just ignore, just calculate the magnitude first. Okay, now the R here, the distance, this one distance is 5 centimeter. So you get how much? 28.8. Okay, so we have already calculated the magnitude. So now we want to resolve it into the x and y components. Okay, so again, over here, when you are resolving, it is always easier if you write down it in a table. Okay, so this is your E. Okay, so we have E1. E1 just now, how much? 33. This one is pointing this way, isn't it? Then we have the E2 is in this direction. Okay, so this direction, so that's what this one only horizontal, so this is 0. I'm going to check the conventional x and y axis as positive. Okay, so I always compare my component with this. If it is pointing in the opposite direction, then I will put a negative sign. If it is in the same direction, positive. Okay, so this one pointing to the right, so it is a positive. All right, and this I will have to resolve. Yeah, remember I said I resolve, I will get the, this is your x, okay, then I will get the y. So this one, the magnitude is 28.8. Okay, so this one, let's say this is the angle. So again, this one is cos, okay, cos theta, and the other one will be sine theta. Okay, so cos is adjacent, sine is opposite. Now I look at the direction. The x is pointing to the left, right? The y is pointing downward. It is opposite to what I have indicated, my direction. Look at the one in curvy circle, okay? So y upward is positive, so that is why this one I have to put a negative, okay? And this one I also put a negative here, all right? So I will have cos is 4/5. So this one is sine 3/5. Okay, so I calculate this, I'm going to get how much? 23.04. And this one, I'm going to get 17.28. Okay, so the negative means that it is pointing to the left. And negative for y means that it is pointing downward. Okay, then after calculating this, I'm going to get the net for x component. Oh, this is negative, so I minus, all right, 23.04. Okay, so this one I am going to get 10.71. Okay, so it is positive, so where is it pointing? Positive, then I refer to my direction, pointing to the right. Okay, and when I calculate the net for y component, I have 0 minus 17.28 times 10 to the power of 3. So I'm having negative 17.28. Okay, so I get this. All right, so this one means that it is pointing down. Okay, so after that, after getting this, then I'm going to calculate the net. Oh, this should be E, yeah, sorry, E. Okay, so I'm going to calculate net square plus. Okay, so you substitute all this in, then you are going to get 20.3 times 10 to the power of 3 Newton per Coulomb. Okay, so you are going to get this. And the direction will be like this, yeah? Direction, you can just draw this one. Okay, this is your EX, right? Pointing to the right. And your EY pointing downward. So where is your E net? E net has to be in between the EX and EY. So your E net will be here. Okay. So this is your E net. So if you want to get this one, let's say you want to get this. So alpha will be shift tangent EY over EX. Okay. Ignore the positive and the negative. Just use the magnitude. You will get the answer. Yeah, I'm going to quickly calculate this. EY 17.28. EX is 10.71. Okay, so I'm going to get see this angle is the same as the one that this one is the same as the one that we have calculated just now. Yeah, if you remember, 58.2 degree. Okay, and but this is not the final answer, because the final answer eventually it wants us to oops. It wants us to determine the electric force experienced by the positive charge. Still remember, the electric force is E equals to F divided by Q. Okay, so here we want to calculate so E equals to F over Q, right? So here is what we need to calculate the F. So we want to determine the electric force. So electric force equals to QE. Okay, so the charge is the charge is what, 2 nano, right? Then the E is 20.3 times 10 to the power of 3. Okay, so if you calculate this, you will get 4.06 times 10 to the power of negative 5 Newton. Still remember this value? 4.06 times 10 to the power of negative 5 Newton is the one that we have calculated from our work example 1. Okay, so you will notice that if we want to calculate electric force, you can directly use the equation for electric force, which is K Q1 times Q2 divided by R squared, or you can calculate from electric field first, then you use this equation. Okay, electric fields is actually the force felt by a test charge. Okay, so F divided by Q. From here, you can also get the electric force. Okay, all right. So electric field patterns. Okay, so remember, it is always pointing radially outward from a positive charge, but then radially inward into a negative charge. Okay, but if you have two positive charges together, like this one, yeah, like this one, you have two positive charges, then you see here, inside here, this one, here, inside them, okay, the electric field is 0. Okay, so this is how the charges are being arranged. Then you will have different electric field patterns. Okay. Okay, another very important one is to introduce you to conductor. Conductor is the material that can let this electricity, go, right? Okay, so electric field inside a conductor is actually 0. Remember this, yeah? Electric field inside a conductor is 0 at a static situation. So electric field outside the conductor, okay, outside the conductor, you will still have the electric field, and it is always perpendicular to the surface of the conductor. So let's say you look at this, this is like a circle, right? So outside, your surface is here, is the circumference, right? Then you see the electric field, always perpendicular, 90 degree, pointing radially outward. Okay, and any excess charge will reside entirely on the surface of the conductor. So this is a very important discovery, because it can this information whereby the electric field inside a conductor is 0 can be used in different applications, especially to protect human. Okay. Yeah, so here, electric field in a conductor are Faraday's cage. So just now we say inside a conductor, the electric field is 0. So the field is only outside. Okay, so there are two links here. The first one actually not working anymore. So I have found another one. the second one. We don't have much time, so can I get you guys, okay, to watch this one on your own, okay? Watch on your own, yeah? This one, very short video, less than 2 minutes. It actually did an experiment by putting somebody inside the cage, and then notice that the electricity, it doesn't go to the person inside the cage. But when there is no cage, then the person will feel the electric field. Okay. All right. So this one, I want you guys to watch it on your own. Okay. So this is actually discovered by Faraday in 1830s. That the interior of a metallic cage, metallic normally is a good conductor. Okay. Metallic cage or mesh shields. Then the external static electric field can be it doesn't go in. Okay, the electric field doesn't go within the conductor because the field causes the electrons in the metal of the cage to shift. Okay, so you will you look at the cage here. The negative now all shift to the left hand side, the positive to the right hand side, because electric field is pointing from left to right. Okay, so left hand side pointing upwards is from a positive charge. So positive, then the negative will be attracted. Okay, then the other one is the other way. All right, so positive, they will run away from the positive charge, but negative will be attracted. Okay, so the electrons, they rearrange themselves in the conductor. So Faraday cages are used to protect people and equipment from lightning strikes or from electric discharges. They are also used in sensitive experiments, especially those who are dealing with testing electricity or something like that. Then they don't want the interference from the surrounding. Then they also have to conduct their experiment inside a Faraday's cage. Okay. Right. So this one, you see the electrons that the positive and the negative charges, they rearrange themselves. Okay, so the electrons, they will move to the positive side because attract, then the positive will quickly run away from the positive. Okay, so they will run to the right hand side. All right, so some application, automobile and aeroplane. Okay, the compartments are essentially Faraday cages. Okay, protecting the passengers from electric charges. So maybe you have you inside here, then you are protected. Okay, or maybe in a car also. Okay, in a car. Okay, in a car, you are here also protected. Okay. Then elevators and other rooms with metallic conducting frames. This one simulates a Faraday cage effect, leading to loss of signal. Normally in a lift, elevator, then you feel that your phone no sign, right? So that this is called dead zones. Okay. All right. Some application. Okay, we want to quickly move on. Okay, what's wrong? Oops. Oh, sorry. How come hang on, yeah? Okay, if it is like this, I will stop sharing, then I go back to the slide again. Oh dear. Hang on, yeah. Okay, I go to the next slide. Then I okay. All right. Just now we said electric field inside the conductor is 0. So now if we have two parallel plates, okay, you have two parallel plates, then the electric field between the charged parallel plates is always uniform. So one side, the left-hand side is positive, the other side is negative. So you see the electric field is all horizontal, right? Uniform. They will also be evenly spaced between them. This one is evenly spaced here, you see? Evenly spaced, so they are uniform. And then if you have, this one is high voltage, or you can say high potential. A negative one is always the one with low potential, yeah? So you have the positive side with high potential, the negative, the other one, low potential, then we can actually compare the potential difference, okay? That is why you have the delta V. This one is potential difference. Or we can call it voltage, okay? So the uniform electric field in between two plates, instead of just now we said E equals to F over Q, right? For two parallel plates, then you have this one. Okay, so the V is the potential difference. The D is the distance between the two plates. Okay, so this one is the potential difference. And this one is the distance between them. Okay, between the plates. Okay, oh, it's already written down. All right. So electric field between two parallel plates. Let's say, yeah, you have there is an electron gun. It has parallel plates separated by 4 centimeters. Okay, so you have two plates like these. So the distance here, D is 4 centimeters. And it gives electrons 25 kilo electron volt. Okay, this one EV, okay, is electron volt. Later on, you will come to this, okay? Electron volt is also a unit to tell about the energy, okay? And then 1 electron volt, okay? 1 electron volt equals to 1.6 times 10 to the power of negative 19 joule, okay? So electron volt, because normally the energy possessed by a charge is very small. So if we use joule, it's too large, okay? So that's why they have this electron volt to as another unit to tell about the energy, okay? So 1 electron volt equals to 1.6 times 10 to the power of negative 19 joule, right? So it gives electrons this much of energy. So what is the electric field strength between the plates? And what force would this field exert on a piece of plastic with a 0.5 microcoulomb charge that gets between the plates? So the second part is, let's say you have a charge here. You have charge. Okay, so first of all, we know that for two parallel plates, the electric field equals to the delta V divided by the D, right? By the distance. So now we want to calculate this potential difference. Remember just now we said today we are going to learn 4 new terms: electric force, electric field, electric potential energy, and then another one is electric potential, right? So this one V is actually electric potential. So maybe here, since we need to use it, so I will just introduce to you. V equals to, this U is electric potential energy, okay? This one V equals to U divided by Q, okay? This one later you will learn about it, but we just introduce first because we need to use it for this question. Okay, so before we can get the V, because it doesn't tell us about V, it only gives us about the energy, which is in electron volt. So we can get U, okay, we can get U, and then it says this is electron. So the charge for an electron is 1.6 times 10 to the power of negative 19. Okay, electron, the charge for an electron, okay, electron, yeah, is 1.6 times 10 to the power of negative 19 coulomb. Okay, so from here we calculate V first. Okay, so how do we get V? Is U divided by Q. Okay, so how do we get U? U is given as 25 kilo electron volt. So 25 kilo, what is kilo? Times 10 to the power of 3, right? Electron volt. This is electron volt. So just now I said 1 electron volt equals to, so we want to change it to joule. So remember how we do unit conversion? 1 electron volt equals to 1.6 times 10 to the power of negative 19 joule. Okay, I want to keep joule. I don't want to keep as electron volt. So this is just the U. Okay, this is just the U. What's the Q? Electron, right? I say gives electron. It gives electron. So electron, the charge is 1.6 times 10 to the power of negative 19 coulomb. Okay, so from here, you can get your delta V as 25. Oh, this one 1.6 times 10, you can cancel, yeah? So basically, you get 25 kilovolt. Okay, you get 25 kilovolt. Then we can substitute into E equals to delta V divided by D to get the electric field. So electric field equals to how much? 25 kilo, okay? And then divided by distance is 4 centimeter, so 0.04 meter. So you get 625 volt per meter. Okay, or you can say 625 kilovolt per meter. Okay. So this is how we get the electric field between two parallel plates. It has a another formula, which is E equals to this one. Okay. And now the second part, B. This is A, yeah. And then B, what force would this field exert on a piece of plastic? This one is where we use this. Okay, so now we want to get F, so it is Q multiply E. So what is Q? 0.5 micro. Okay, micro is negative 6, and then times E is 625 kilo. Okay, so we have 0.31 Newton. All right. Okay. So this one is electric field between two parallel plates. Okay, we quickly move into electric potential energy. Electric potential energy we can calculate for only one charge, or we can calculate for the whole system. The whole system may have a few charges, okay? So how do we calculate this? Actually, electric potential energy of a charge is the energy that the charge has because of its position relative to other charges, okay? For example, you have a charge here, then there are some neighboring, maybe neighboring, some positive, some negative. So just look at this one. What is the electric potential energy that this charge have due to its neighbors? Okay, so this one is only talking about the charge. But if for a system, then you consider everybody inside. Okay, consider all the charges inside. Then you have to compare, okay, this charge with another one. Let's say this is O, okay? Then you have a 1 here, 2, 3. So if for a system, then you have to compare, okay, between 1 and 0, between 0 and 2, between 0 and 3, between 1 and 2, between 2 and 3, between 1 and 3. You have to compare everyone, okay? But if just comparing one charge, then just compare that charge with the neighboring, all right? So that is the difference between potential energy for a charge and for a system, okay? So electric potential energy has a symbol of U, and it has a unit of joule, all right? So let's go to the formula. See here, K Q1 Q2 divided by the distance between the charge 1 and charge 2. Is it very similar to electric force? It's very similar to electric force, okay? Electric force is, let's say 1, 2, yeah? It is K, Q1, Q2, and then R1, 2 square. It has a square, but electric potential energy, there's no square, just the R, all right? Okay, so this one is just calculating the electric potential energy on Q1 due to Q2. This one also similar. If it is on Q1, then we write down 1 first, due to 2. If it is electric potential energy on Q2 due to Q1, then you will write down as U21. Okay, on which one, then you write it first. Okay, then due to the other one, then you write it second. So it is K Q1 Q2 divided by R, just R. Okay. Now electric field and electric force, they are vector, right? So they have magnitude and direction. But for electric potential energy, this one should be U. It is a scalar, so there is only magnitude. Only. Okay. So when it is only magnitude, then when you calculate, important, okay, has to be included. Okay, just now we said for force and electric field, we don't want to include the positive and the negative sign of the charge in our calculation for E or F first. Just calculate magnitude. Later on, then we add in the positive or negative to represent the direction. But since electric potential energy is a scalar quantity, then the positive and the negative sign of the charge has to be included directly in the calculation. Okay, so this one have to be included directly. Okay, we'll quickly move into the example. Okay, still the same diagram. Okay, today you are going to deal with this all day long. Okay, so what is the electric potential energy of a positive charge position at O? This one, just the charge. Just considering the charge, okay? So we consider the charge first. What is the formula? U, right? So let's say this is O. On O, due to, there are two neighboring charges. One is Q1, one is Q2. So due to this one, and you have to consider for due to Q2, okay? Because there are two neighboring charges for all, right? So consider both of them. Okay, so we write down. Okay, what is the K? Can say QO, Q1, and then R. This one is O1. Okay, plus K QO, Q2, RO2. Okay, K is this one. QO is what? Okay, positive. This one positive. All right, 2 nano. Q1 is also positive, 6 nano. All right, and the distance is 0.04. How about the other one? 9. Okay, this one is 2 nano. But then you look at Q2. Q2 is a negative charge. So include the sign as well. Okay, so this one is, so remember this one is 5 centimeter. Okay, so you calculate this, then you are going to get negative 1.8 times 10 to the power of negative 7 joule. Okay? All right, so this is for a charge. Now we want to quickly move on to for a system. Now, if for a system, you look at the whole thing, right? Look at the whole thing. Then you have to compare, okay, between Q1 and O, between Q1, between O and Q2. Then you also have to compare between Q1 and Q2. Okay, remember for a system, compare everything. All right. So B, for a system, okay, this one is a system. Then you will have O with 1, and then you have O with 2. Then don't forget about 1 and 2. Okay, so this one O and 2 at position O and 1 and O and 2, we have actually calculated from previous, right? This one from just now, O1 and O2. So this is K QO Q1 and then RO1 plus K QO and Q2, and this is RO2, and then K Q1 Q2 R12. Okay, 9 O is what? 2 nano. This one is 6 nano. Don't forget the negative, yeah? Q2 is a negative charge, nano. This one is 0.05. Okay, then you plus another one. This is 6 nano. That one is negative 8 nano. And the distance between them is 0.03 meter. Okay, so this one you calculate, and then you are going to get negative 14.58 times 10 to the power of negative 5 joule. Okay, so this is for a system. All right, so we have potential, the last part. So I will continue this one tomorrow during tutorial. Okay, so if you have any question, then you guys ask tomorrow. Okay, so I will stop here and we will continue this during tutorial before we discuss the question for tutorial workshop. Okay, and for those groups you haven't shared your group, the Google Drive, quickly share it. Okay. Okay, so that's all for today. I'll see you guys again tomorrow 11:30. Where to check your midterm mark? I think midterm, I'm not sure whether Miss He has finished already. But I think she will announce. Okay. Yeah, maybe she hasn't finished marking yet. All right. Okay, so I was where to check the comment for project. You go to Moodle. Under every week there will be announcement, right? Announcement is on the Moodle front page. You go to updates for project. Then you look at the comments. Okay. Under updates for project, look for the comment for your group. All right. Any question you guys ask again tomorrow. Okay. So thank you for joining this session. I'll see you guys again. Yeah. If you have already shared the Google Drive, then never mind. Only for those groups who haven't shared. Okay, bye-bye. Thank you, everyone.